Okay, hello everybody. My name is Afak, and we're going to be taking a deep look today at text-to-SQL systems. We're going to be taking a look at how they're evaluated, as well as the data sets that have more shaped the field, and then finally we'll take a look at how modern large language models have been able to change how we perceive text-to-SQL benchmarks. How do we go about evaluating these, and different prompting techniques we can also go over to improve the accuracy of these text-to-SQL models. So this presentation is divided into two distinct parts. The first one will talk about benchmark datasets and evaluation metrics, and then the second part that we'll go into later focuses more on large language models and the prompting techniques that can make them best suited for text-to-SQL. Right, so to go over first of all, why do we have these benchmarks? Well, to understand a text-to-SQL system's performance, we need a bunch of standardized data sets. These different data sets can stress different skills. So like domain coverage, can like you apply these to all different sorts of scenarios. The SQL complexity and multi-turn interactions. So like, can you parse a single question versus go into a conversation and parse the context of what the user has said in the past to form your query? Right? We also need these, good metrics that can reflect semantic correctness and not just string similarity. So two strings, for example, the two I've listed here, and a couple of more examples I'll get into, can look different but essentially provide the same answer, right? So these benchmarks and metrics can define what we consider to be good models, or solve data sets as well. So if a model can solve a data set. So two early benchmarks, and Andrew did touch on this in his presentation a little bit, but ATIS and GeoQuery, these are from the 90s and early 2000s. So ATIS, Airline Travel Information System, talks about flight connections, flight times, prices, and so forth, right? There's about 25 tables and a good chunk of natural language to what we now have as SQL pairs. A couple examples, like give me a 6:30 a.m. flight on August 27th from Atlanta to Dallas, is transformed into language that the system could understand, but we could later map to SQL. Right? It's relatively small within a single domain, and any models can achieve pretty high accuracy with these. GeoQuery, that's another one, mostly focuses on US geography, so like rivers, states, borders. About 880, so relatively smaller logical form pairs, which were mapped to SQL later. So a few examples were like, could you tell me the capital of Texas? And this would be the logic associated with it. Or what states border the state that borders the most states? That's a good example of like a nested query. And I guess extra points to you if you happen to know that answer. But the issue with these is that a model that like completely solves ATIS and can get every single query perfectly could fail entirely on a different domain, like a medical database or e-commerce or anything like that, right? So a couple other limitations, the small number of examples, only hundreds or a few thousands, doesn't necessarily cover the sheer number of possible combinations that can occur, right? Anyone who took 1805 can think about like, oh, how many combinations of all these SQL queries can be made? It's going to be absolutely huge, right? So having only 100 or a few thousand examples might not be the best to cover a more broad spectrum. A single domain results in like a poor test of cross-domain generalization, mentioned that earlier, and the fact that the SQL is relatively simpler means that there's not a whole lot of training data on like joins, aggregation, order by, etc. Right? These also have a risk of overfitting and benchmark saturation. What I mean by that, I'll give a few examples right here. So overfitting is when you have, if you haven't taken ML yet, I haven't either actually, but it's when you have a model that can describe a situation too accurately and then doesn't generalize well. So you want like a nice happy medium between generalization and being very specific to the data that you want to model. And benchmark saturation is a real life example. It's when everything is performing so well that it's hard to discern between which one's actually doing better than another. So, if everyone in Ontario is getting like 90s, high 90s in high school, how can universities figure out what students are the best to have in their program? So it makes admissions more competitive, and it's a lot harder to discern, which students are good. That is more of a real life example of benchmark saturation. Right? So To rectify some of these problems, we also have WikiSQL. It was a bit of a larger breakthrough in 2017 by Salesforce, over 80,000 examples from many different Wikipedia tables. So it allowed neural networks to train at a much larger scale. Issue with this, though, is that WikiSQL only contains single table select queries. There are a whole bunch of larger tables, but the queries don't merge or group other tables with one another. So there's a lot of variation in schemas, but not a whole lot of complex SQL queries. So models that could work great on WikiSQL and have, one part of it handled might fail whenever you throw in some multi-table queries. And this is just an example of what the training data looks like. It's associated with some table ID and then a question, and you can select from within that table that's provided. So, counties with median household incomes, it just tests whether the model is able to select from within that table. Or Lithuanian national badminton championships, or who played guard for Toronto in 1996. Very broad spectrum of possible questions that we can see here, right? So in comes Spider, which is a lot more complex. It's cross-domain, completely redefines text-to-SQL because it has thousands of questions across 200 databases, and each with their own schema. You have much more complex SQL queries involving joins, aggregations using group by, nested subqueries, set operations. This requires models to adapt to new schemas just as you would in real life. And when this was first introduced in 2018 by Yale, the best models would only get around a 12% exact match. So it was very challenging at the time. And I say at the time because we'll see in a bit what's happened now. But it has driven, a lot of huge research progress with this very vast data set that models were able to train in. Right, we'll get back to Spider in a bit, but just to kind of tangent off a little bit, we also have a few offshoots of Spider and WikiSQL. So Wikitable questions has questions and answers on Wikipedia tables. They're just question and answer pairs, so not necessarily SQL, but that could be helpful in some circumstances. Spark, or SPARC, however you're supposed to pronounce that. It is a multi-turn context-dependent SQL generation. So it's an offshoot of Spider, but in this case, it requires you to parse through context, multiple turns of context, rather than just find me this. Now find me this separate thing. It requires that context of the previous user. CoSQL is conversational text-to-SQL. Once again, even more conversational, requires more context than Spark, has less dialogues, more turns, and then, around 10,000 SQL queries itself. And then you have MultiSpider, which is a multilingual version of Spider. It's the largest and highest quality multilingual text-to-SQL dataset, covering 7 mainstream languages: English, Spanish, German, French, Chinese, Japanese, and Vietnamese. And it tests whether methods generalize beyond regular English and require handling language-specific phenomena like word segmentation in Chinese. You can see instances where some models might be making lexical or structural mistakes that wouldn't necessarily appear in English just because it needs to be translated or those tokens needs to exist in other languages as well. So in this case, it's mixing Führer des Landes with Staatsoberhaupt, which is the head of state. So that's what it should be, and then in this case, it finds the form of government instead. So, or in French, quel est le modèle de voiture avec le MPG le plus élevé? What is the car model with the highest miles per gallon? And in this case, it confused, car or modèle in this case with maker, even though the correct response should be from the model schema. Right, so a couple lexical and structural mistakes, or in this case, it's sorting by ascending. It should sort by ascending when it actually sorts by descending, right? So, just to kind of recap everything that we've touched upon so far, some of the dimensions that we need to consider in our data set. our domain, SQL complexity, interaction level, the language, and the size. And you can see where each of the different, data sets we've talked about lie on these axes. We talked about domain. Well, WikiSQL, it has a whole bunch of tables, but all the queries only focus on a single table at the time. So it is the most single table. At least GeoQuery and ATIS might focus on other tables as well. CoSQL and Spark being, basically the same as Spider here. They're all super, super cross-domain, right? They can handle a whole bunch of different, I think it was 200 schemas to choose from and join as necessary. And Spider and CoSQL Spark, they also win in terms of like SQL complexity, right? It has complex joins, aggregation, and subqueries, whereas something like WikiSQL only focuses on like projection, so like the select keyword, interaction. All of these, ATIS, Spider, WikiSQL, GeoQuery, they mostly focus on singleton. Can you answer this one question in the context of this, only this single question? Whereas Spark might follow up with a few extra questions, and CoSQL is almost entirely dialogue based. So once again, that would be a good data set to train on for that specific instance if you want to analyze how well it can handle interactability. For language, a lot more straightforward. All of these are basically monolingual: ATIS, Spider, WikiSQL, CoSQL, Spark. They're just in English. GeoQuery, there are translations, so I guess, but they are still like, they're not English, right? There's also other translations of it, but for the most part, not truly multilingual. Whereas Multi-Spider is designed to be multilingual. It's a multilingual version of Spider. And then size. GeoQuery being the smallest, ATIS slightly larger with a bit more training data, but WikiSQL is by far about 8 times larger, I believe, than Spider, right? So huge corpus of data to go on with WikiSQL. So they all have their certain advantages depending on what you want to use. And this is another such graph kind of illustrating this. This is on Spider's website talking about like, the numbers of tables, the number of nested having. As you can see, Spider mostly covers that, aggregation, group by, order by, having, so forth. WikiSQL, though, has just a larger number of pure SQL queries and pure number of database instances available. So moving on from there, now that we've seen the data sets, how do we actually evaluate a model's SQL prediction? There are a couple of main metrics that we can use, being exact match, which is the, very strict. It's basically just look at the string, see if it matches. Exact set match, which is used by Spider. Execution accuracy, and diagnostic metrics like, component, the specific components of which, SQL keyword is being used, or how many turns are actually being processed. So those are extra diagnostic metrics that we can use on a case-to-case basis, and we'll go into depth on each one right now. First one we're going to take a look at is exact match accuracy. This is the percentage of predictions whose SQL is exactly the same as the reference SQL string. So early works like ATIS, GeoQuery, they'd often use this because the data sets were small and the queries were pretty much less varied. It's a lot easier to say, hey, this is a single source of truth. There's not a whole lot of variation we could use. So they're good for like a sanity check, but they're not necessarily the most correct. And by correct, I see like they capture the full correctness of any particular query, right? So we ask, is it identical? It's very simple, easy to compute, understand, literally just like, are they the same? If not, probably super easy to program. But it can, generate false negatives very, very easily, right? It penalizes benign formatting differences. So, if you switch up the orientation of the greater than less than symbol, all of these could break exact match accuracy. So it's not the best metric to define whether a SQL query is truly correct, right? Another thing that we can use is exact set match that was introduced by Spider. It compares sets of components like select, where, group by, etc., while ignoring the exact ordering and formatting. So it's a lot more broad and encompassing than the exact string matching we had earlier. So it's a lot closer to semantic correctness, but it's still not perfect, right? So for example, if you decide to use a join where the gold SQL would wouldn't have it, right? That would fail. It's equivalent logically, but it's still written in a different way because it doesn't use the exact components, it doesn't use the same SQL keywords as the gold standard does, right? So still precise, focuses more on logical equivalence, but not perfectly. Next, we have execution accuracy. So execution accuracy executes the predicted SQL and the gold SQL in the database. If the result sets match, then the prediction is counted as correct. So, it just runs the gold predicted and gold SQL against the database and checks if the two of them match. It directly measures whether the model answered the user's question, but two wrong queries might coincidentally return the same result on a specific database, and you wouldn't necessarily know if that was the semantically correct to the question that the user asked. Good example of this that I want to throw in was the feedback I got for one of my assignments, where the query's logic was incorrect, but I didn't notice that at the beginning because when I ran the queries, it still returned the data that I expected. So it didn't necessarily solve the user's question exactly, but for that particular database, it worked perfectly fine. So, Spider does a very good job of making sure that they have carefully designed DB instances that prevent these sort of false positives when it comes to execution accuracy. So while the others might suffer from false negatives, this one has false positives, so to speak. So a couple other metrics that we'll go over: component level accuracy. It basically checks at the level of each clause. How well does the model do with projections like select? How well does it do on where, join conditions, group by, order by, etc.? It checks each individual level as a metric. And for multi-turn data sets, so like CoSQL, conversational SQL, or Spark, just takes a look at multi-turn accuracy or whole dialogue success. These metrics help researchers pinpoint which parts of their SQL they might need to target a little bit more. But for the most part, most research papers will stick to exact set match evaluation accuracy as their primary metric. At least that's what Spider does as well. They kind of stick to exact set match and evaluation accuracy in their leaderboards, and these are the leaderboards. I'm not going to go over all of the individual rows here, but essentially what Spider focuses on is the execution with values, checks what percentage of the gold and tested queries match, and then exact set match as well. Right, making sure that without considering the actual values that it records, just making sure that the query is structured the same logically. Okay, so from here we can kind of see the progress that has been made. Spider being very initially hard. This graph that I put together doesn't show it, but back in 2018, the best models would only get I think it was 12 or 20%. But as we continue, 2020, they start to get better, and these are the non-large language model based approaches. But around 2023, with the release of GPT-4, GPT-3, we start to see some major improvement gains being done on the LLM side, reaching near 100% execution accuracy on the entire database for Spider 1.0. So, if performance started to skyrocket and we realized, hey, if GPT-4 is getting crazy amounts on Spider, what do we do from here? Well, you create another database. you create another data set. Spider 2.0 is used mostly to now evaluate how well LLMs can do. And you can see over literally the past year, this is this graph starting with GPT-4o a year ago, seeing how well models like Claude, DeepSeek can do when partnered on their own, and with specific agents that can handle some of the tool calling and parsing of the data as well. So we can slowly see that we're once again starting to reach very high accuracy, moving into more recent models like Native Mini, which about a week ago managed to hit roughly 70, almost 80% accuracy. Right, so that leads us into part 2 right here, large language models, prompting techniques for SQL. And I guess this concludes part 1 if you just want to listen to the benchmarks and whatnot. But Moving on to LLMs and prompting for text-to-SQL. Before LLMs, things were very highly specialized in our architectures. We had very specific encoders for questions, schemas, grammar-based encoders. But a good thing and a powerful implication of LLMs is that they can just generate SQL. They don't need training on your database, right? They can, and this is what we call zero-shot prompting. It's like, I guess not even prompting at this point, just gives the model a task with the instructions and relies on whatever it's already been trained on, right? So GPT 3, 4, those early models, they were pretty good at that. Focuses are shifting from like training these very narrow models that we had before LMs to just prompt engineering to make the most out of these huge amounts of data that GPT has already been trained upon. What's even better is that we can, supply a few example pairs. We'll call that few-shot prompting, and the model uses them as a template to answer more questions. So it's allowed GPT-4 when it first started out to just jump straight to Spider without having to train all that much. So a couple prompting techniques that, some of you guys might already use this whenever working with SQL stuff. So I'm not going to go too in depth about this one because there's space for that later. But without the schema, the LLM might like hallucinate model or table or column names, right? So, large schemas means more context tokens and whatnot. So, there's some issues with this schema condition prompts, but the basic general kind of thing that I wanted to get into here was whenever we want to prompt an LLM with this kind of stuff, we should specify the available tables, the columns, describe relationships that occur in the database, keep your schema text concise because, there is a limit to the number of tokens it can hold physically, which means you might need to prune or use retrieval, which we'll get into later as well. And just to make sure that the LLM here knows exactly what it has, what resources it has available, and uses only those things and doesn't just make something up. So, example of a good prompt right here. I just kind of wrote this. I'm sure GPT would do something similar. Something else you can do, as we mentioned a little bit earlier, few-shot patterns. So providing a couple high-quality examples before the actual question, because, LLMs, they match patterns. They infer the output format based on the probability. They're all rolling a bunch of huge dices and doing matrix multiplication and whatnot. They're, getting through those typical reasoning steps from the examples it was trained on. So give it a little bit more. Keep the examples kind of similar in style and complexity. So maybe even having a nice healthy mix as well of like projections, joins, aggregations, group by, nested subqueries. Some systems might automatically choose examples from training data that are similar to the current question, through embeddings. It improves correctness, especially for queries that resemble the examples that are already provided. Chain of thought prompting. So, a lot of models now have chain of reasoning kind of built in. You ask GPT-5 something or GPT 5.1, it'll either answer your question automatically, it'll kind of ruminate and think over the question a little bit before providing you an answer, right? That's chain of thought reasoning. So try and encourage that LLM to think step by step, create that reasoning. It helps the model pick the right tables and joins by making its reasoning more explicit. And even if it doesn't actually show the reasoning to end users, usually that internal chain of thought will, by default, improve accuracy, right? And those LLMs like GPT-5 can already decide how much to think. Now, one problem with LLMs is, as we've already mentioned, they generate invalid SQL or reference columns that don't exist. It'll just hallucinate something. Picard, hopefully pronounced that correct, solves this by validating each token as the model generates SQL. So it'll kind of pick each token one by one, or not necessarily one by one, but parses the output and just rejects tokens that would break the SQL query or that don't actually exist in this schema. And it's led to some pretty improved performance with T5 on Spider and conversational SQL. So it reduces hallucinations and syntax errors, which is nice. Now, moving on from there, we also have LLMs that involve feedback or execution-guided approaches. So it's kind of analogous to how a human might debug, run, take a look at what's there, and then fix it. Generate candidate SQLs, execute them, and then discard those that error or return suspicious results. Kind of an extension of what we mentioned already with Picard. So, if we have self-checking prompts, so is this SQL correct? If not, fix it, right? You can run through sort of a pipeline of SQL query generation and make sure that you check your steps over and over to make sure that the query is actually correct and you're not just hallucinating something. And something else that LLMs can do nowadays is tool calling, right? So LLMs can write SQL and then have send out a little bit of JSON or some JavaScript thing to run a tool call, get the LLM to see the result, and then revise the query as necessary. It does require multiple tool calls, but you can hook up an LLM to the DB engine to use it as feedback tool, and that's kind of mimicking how humans debug SQL and can help increase reliability here. So, some LLMs that we have that employ tools and specialized models. A great example of this is SQL Coder. It's a 15 billion parameter model open sourced by defog.ai. They trained it pretty extensively on SQL examples, and it does show some pretty impressive results. It even beats some much larger general models on SQL tasks. Another powerful idea is letting the LLM use tools rather than doing everything in its head. Think of an AI that can consult a database schema, as we mentioned already, or execute a query to check its work. There's an example of the Gorilla project, which I don't have in the slides, but I will have for the presentation, exemplified this by allowing an LLM to call APIs with the help of a retrieval system, right? In Text-to-SQL, similar agent frameworks exist, so the LLM becomes a controller that can perform actions like looking up table info, running the SQL that it wrote, and then correcting itself. It's great for reliability. If a model's unsure about a column name, it could query a schema dictionary rather than just hallucinate it. So we'll dive a little bit deeper into how these LLM-driven agents work, how they bring the robustness of our traditional programming that we're used to in the loop, making the system a bit more dependable on real databases and not just at the whims of whatever the LLM feels like saying on a particular Tuesday, right? Modern text-to-SQL systems will often plan first, then generate. So instead of directly just spitting out the SQL, the LLM or a set of LLM-based modules will first figure out a more high-level game plan. So what tables are involved, or how to decompose a more complex question into similar parts. Kind of like writing out an outline before the actual SQL code, and what we talked about earlier, showing that chain of thought reasoning. So studies have shown that this approach does improve correctness in this planning. The model is less likely to hallucinate column names or join tables incorrectly. So one example here is SQL Genie from 2025, very recent. It'll split the text-to-SQL larger task into a bunch of task-based agents, which will take on different aspects. So the planning agent is the one that will start to ask clarifying questions, making sure it has all the information it needs to solve the query. It'll pass this stuff over to an answering agent, which uses internal documents, the web, all the resources that's available to the agent to answer those questions. The answering agent will pass it on to the generation agent, which builds the SQL query out itself. That'll be passed over to a critic agent that evaluates the query, sends feedback to the debugging agent, rinse and repeat over a length of t time or a number of m intervals or anything, however you want to define that, right? It results in much more accurate queries, but can be impractical due to high computational costs. So as you increase the amount of time you're given it, the amount of computation required, or the amount of repeats that, if you increase the number of repeats that you're allowed to do, that time will increase drastically, but you will start to see at least some returns in execution accuracy, right? Another example is MaxSQL 2025 framework, where multiple agents also collaborate. One agent breaks a complex question into subtasks like, find the eligible customers, then calculate their total spending, as an example. And then another agent will focus on the relevant subset of the schema. And the final agent, the fixer agent, will fix any mistakes by actually running or validating the SQL. Once again, this results in a much higher success rate on complex queries, since the system can iteratively correct itself and handle the complexity step by step. There is a speed trade-off, but makes it much more accurate. So new frameworks like DSPy treat an LLM-powered workflow as a programmable pipeline. Instead of a single huge prompt, you build a bunch of small modular functions or stages that will pass data to each other. It's analogous to breaking a program into subroutines, standard software engineering principles. So you define a signature, like a function signature, to specify input output for each step and then implement those as module classes. So one module might take a natural language question and output a clean structure form. Another module takes that and the schema and crafts a precise prompt. And the final module calls the LLM to get SQL. And each of these modules can be tested on their own. It makes the text-to-SQL system a lot easier to debug and maintain. If the SQL generation step is making mistakes, you can inspect or tweak that module without touching the rest. You can log intermediate results, what was the plan, what did we retrieve, in order to understand failures. So DSPy and similar frameworks come with tools to improve and evaluate your pipeline. So, DSPy's teleprompt can auto-optimize prompt wording, and evaluating utilities let you measure the accuracy of the SQL outputs more easily. It means you can iteratively refine your text-to-SQL system in a very principled way, just like you'd try to optimize, regular code. It makes LLM usage a lot more like normal programming. So another couple examples to throw in are like Microsoft's prompt flow or a bunch of libraries like LangChain. They let these developers compose multiple LLM calls and tool calls with very structured logic rather than relying on basic prompt engineering. Right? So designing that pipeline of steps that can be tested and improved, which is probably more sustainable for complex applications. Another big theme, retrieval augmented generation, basically feeding the LLM with that helpful context retrieved as needed. So, modern text-to-SQL systems use that retrieval augmented generation to give the LLM only relevant slices of the database schema. I'm sure there's another presentation that's touching a bit more on that, so I'll keep it very high level, at least here. The system can embed table and column descriptions as vectors, and at query time retrieve the top K tables and columns related to the question. So a couple examples in this case, BigQuery RAG user queries are turned into embeddings and matched against Google BigQuery's table schema. Dramatically prunes the search space and improves accuracy. The systems will, instead of having to deal with an enterprise database with hundreds of tables and having to stuff all that schema text into every prompt, especially with the context windows that, some of the later models might have, instead you can create embeddings for table names, descriptions, column info, and then do a semantic search of seeing like which tables seem related to this question. If the question was like how many active users signed up last month, the retriever might fetch the schema for the users table, maybe like a subscriptions table, and then only hand those to the LLM. That's what is meant by like retrieving the top K tables and columns. Right? So Google's team, they demonstrated that with BigQuery, cutting down on the huge amount of data that gets passed through. Another good use for RAG is few-shot example retrieval. As we already discussed, few-shot is providing a few examples in your prompt before sending it over. So instead of just retrieving the schemas, you can also have RAG retrieve prior examples. So a company that has like a log of questions and correct SQL queries, if a new query comes in, the system can pull the closest question from memory and then show the LLM, here's a similar question we answered before, and here's the SQL we use. So it's a lot more dynamic of few-shot prompting, where you can just like pull those prompts in automatically without you having to include it in the prompt yourself. So, a framework might store, hundreds of chain of thought examples from Spider, and then when that complex new question arrives, just retrieve a few similar reasoning steps that the model can use to imitate those successful examples. So that was a lot of information. Just to kind of recap high level the advantages and disadvantages of using an LLM for text-to-SQL. It drastically reduces the engineering overhead, but you still do need good prompt design, input validation, and result checking. And it provides strong performance even on complex benchmarks like Spider, as we've seen in that graph. Very easy to prototype, reduces that overhead, right? Reliability. Outputs can be sometimes kind of wrong. Huge schemas may not fit neatly into context, which requires us to retrieve the information we only need. You might need to provide the LLM still with examples to fine-tune it for very niche domains, and you also obviously need to consider the cost and latency of those LLM calls. All that matrix multiplication requires electricity on those big old data servers hosted by OpenAI, right? So they bring all these benefits: strong performance, easy prototyping, significant reasoning ability, but also introduce these challenges. So, in a real system, you'd integrate this kind of stuff with access control, transaction management, and of course, like security, right? You don't want to have malicious actor, instead of like SQL injection, just prompt inject your LLM to make it run bad SQL code that could really screw up your database. So a lot of things to consider when using LLMs, but they can be a significant time saver. And that covers the presentation I had for today. Thank you very much for listening. Have a good one.